Now that we've found the frequency responses for a few common types of transfer functions, such as first-order, integrator, and second-order transfer functions, we can compile them in a table for handy reference. This table 14.2 appeared in the third edition of the Seaborg text, but was omitted from the fourth edition, and I'm not sure why, because I think it's particularly helpful. So I've provided it here in the slides for you to reference. The first column shows the transfer function, and the second and fourth columns show mathematical expressions representing the amplitude ratio and the phase angle. The third and fifth columns show the normalized amplitude ratio as a function of omega and the phase angle as a function of omega. The normalized amplitude ratio is shown as a log-log plot, and the phase angle is shown as a semi-log plot, just like they are in the Bode diagram. And the low frequency and high frequency asymptotes of the first order and second order transfer functions are emphasized here. You'll recall that the integrator has a normalized amplitude ratio when plotted on a log-log plot that is a slope of -1 that goes through the point 1, 1, and that the integrator has a phase angle that's -90 for all values of omega. The normalized amplitude ratio and phase angle of the derivative are also easy to find. We just substitute s equals j omega, and we find that the transfer function only has an imaginary part. Since the amplitude ratio is the root sum of squares of the real and imaginary parts, and the real part goes to 0, we're left with just the imaginary part, k omega. Remember that the normalized amplitude ratio is the amplitude ratio divided by k. So this is just the log-log plot of omega versus omega, which of course has a slope of +1. And you can show that the phase angle should be +90 degrees for the derivative element for all values of omega. Table 14.2 continues and includes the underdamped second order transfer function, the left half plane 0, the right half plane 0, a lead lag element where the numerator time constant is less than the denominator time constant, and a lead lag element where the numerator time constant is greater than the denominator time constant. It also shows the frequency response for the time delay. One of the reasons I think that this table is helpful is because it allows us to make the connections between the mathematical expressions representing the frequency response and the corresponding graphical interpretations. And it also emphasizes the low frequency and high frequency asymptotic behaviors, which are the limits of behavior of both the normalized amplitude ratio and the phase angle. Of course, these 11 rows in this table are only a small sampling of the vast number of possible forms that a transfer function can take. However, I want to remind you of a concept that we introduced back on slide 5. The frequency response for any transfer function can be obtained by decomposing that transfer function into simpler transfer functions and finding the frequency responses of those simpler components, and then reconstructing the amplitude ratio and phase angle. If a transfer function can be decomposed into a ratio of products of simpler transfer functions, then the amplitude ratio of the composite transfer function is just the ratio of products of the amplitude ratios of those simpler transfer functions recomposed in the same way as the original transfer function. And the phase angle of the more complex transfer function is the sum of the phase angles of the numerator transfer functions minus the sum of the phase angles of the denominator transfer functions. So now that we know how right and left half plane zeros, how first order and second order elements, and how time delays work, and even integrators and derivatives, we can use table 14.2 to reconstruct the frequency response of much more complicated transfer functions. Another great way to represent the frequency response of complicated transfer functions is to use MATLAB to prepare the Bode diagram. I'll provide you with a script to construct the Bode diagram for example 14.3 that you can later modify to construct the Bode diagram for just about any transfer function you want, and you can use it on the homework and exams. Now, since we can reconstruct the frequency response for more complicated transfer functions, one thing we should do is take a look at the behavior of feedback controllers. A proportional only controller is simply a gain. So the amplitude ratio will be a constant, the gain of the transfer function. And the normalized amplitude ratio will always be 1. Since this gain does not contain an s, when we substitute s equals j omega, nothing happens. The phase angle is equal to 0. Recall that the PI controller transfer function can be written this way, which is a left half plane 0 multiplied by an integrating element. We could obtain the amplitude ratio either by substituting in s equals j omega and then finding the real and imaginary parts, or we can simply take the product of the amplitude ratio of a left half plane 0 and the amplitude ratio of the integral element. Similarly, to find the phase angle, we can take the phase angle of our left half plane 0 and add to it the phase angle of our integral element. The ideal PD controller is just a left half plane 0. The physically realizable PD controller with a derivative filter is a lead lag element. And since the derivative filter alpha is usually less than 1, the numerator time constant is larger than the denominator time constant. We can find the frequency response of this by referring back to table 14.2. For the PID controller, we could either substitute s equals j omega and find the real and imaginary parts, or we could also rewrite this in the series form, which was given in table 8.1 back in chapter 8, so that it is a product of transfer functions that we can find the amplitude ratios and phase angles for by reference to table 14.1. Either way, we can find mathematical expressions for the amplitude ratio and phase angle of the PID controller. The third edition of our text also contained a convenient table summarizing the frequency responses of feedback controllers, including the PI, PD, PD with derivative filter, and the parallel and series forms of the PID controller and the PID controller with a derivative filter. This table is also provided here for your reference. Let's talk about some important limits of the behavior of these feedback controllers. Notice for the PI controller that in the limit as the frequency gets very large, the amplitude ratio is the gain of the controller. For very large frequency, this term becomes the square root of omega tau I squared over omega tau I, which is just 1, multiplying the gain, kc. But for very low frequency inputs, the amplitude ratio goes to infinity. Now let's take a look at the PD controller. Consider the high frequency asymptote of the amplitude ratio when there is no derivative filter on the PD controller. If alpha is equal to 0, then this term only contains omega in the numerator. So as omega gets very large, the amplitude ratio goes to infinity for the PD controller at high frequency inputs. However, when the derivative filter element alpha is greater than 0, then the amplitude ratio for high frequency inputs will be kc over alpha. That is, the derivative filter limits the amplitude of the output so that it cannot go to infinity for high frequencies. What happens to the amplitude ratio of the ideal PID controller, that is, the PID controller with no derivative filter, at very high frequencies? You can answer this question by taking the limit as omega goes to infinity. This figure plots the frequency response for a parallel PID controller with some actual values plugged in for the gain, the reset time, and the derivative time. Notice that when there is no derivative filter, the amplitude ratio goes to infinity for high frequency inputs. Adding the derivative filter ensures that the amplitude ratio cannot go to infinity by filtering the high frequency inputs. Up to this point, we've spent a lot of time describing the frequency response of transfer functions, but we haven't said yet why this is useful. In the next video, we'll introduce a stability criterion that's used to describe feedback control loops based on the frequency response.